All right, we're gonna do some chapter 18 homework, but first I'm gonna do a couple in chapter 17. I'm gonna start with 17.68. All right, so it's what's the molar solubility of zinc sulfide in 0.1 molar NH3? So that is a very difficult question. All right, so zinc sulfide in water, that one is simple. You can easily get that. Zinc sulfide in some concentration of an S-2. And then the third type is zinc sulfide in NH3. In order to do this, you need the KSP for zinc sulfide. Zinc plus 2, S-2. You look up your KSP. And the KSP for that is 1.1 times 10 to the minus 21. Then you have to look at a zinc with NH3, and you find that a zinc plus 2 plus your 4 NH3 will do a KF for your ZN NH3 sub 4 plus 2, and that has a KF value of 2.9 times 10 to the 9th. All right, so in order to do this problem, you have to add these two reactions. And you have to remember that when you add reactions, you multiply the K values. So when you add these two reactions, you see that the zinc plus 2 is subtracted on both sides. So you have your zinc sulfide solid with your 4 NH3s yielding your ZN NH3 sub 4 plus 2 and S minus 2. And the K value for this is going to be the multiplication of your KSP and your KF. So it is going to be about 3 times 10 to the minus 12. So 1.1 times 10 to the minus 21 times 2.9 times 10 to the 9th. And that is 3.2 times 10 to the minus 12. All right, so we see that that is a very small number. All right, so very little is going to go to the right. So when you have your initial concentrations, that's a solid, and that's in 0.1 molar NH3. So this is 0.1 molar. We didn't start with any of that or any of that. We know you can't have zeros at equilibrium. So we know that it's going to go to the right. So minus 4S. S and S, we're looking for a solubility, so I'm going to call it S. And so at equilibrium, you have your 0.10 minus 4S, you have your S, and you have your S. All right, and we see that your 0.1, your initial concentration divided by your K value, 3.2 times 10 to the minus 12, that is much, much, much greater than 1,000. You're talking billions, way more than 1,000. So you do not have to check your answer. You can neglect your minus 4S and go right to your answer. All right, so we can set up that the K is the concentration of products. That is your zinc NH3 sub 4 plus 2. That's aqueous. All ions are aqueous. Your S minus 2 at equilibrium. Zinc sulfide is a solid. We do not put that there. NH3 is raised to the 4th. All right, and so now we just plug in our numbers. our zinc, NH3, 4 plus 2, that's S. S minus 2 is also S. The NH3 is 0.1 minus 4S. We can neglect our minus 4S, so that is simply 0.10 to the fourth, and that is equal to 3.2 times 10 to the minus 12. All right, so then we multiply both sides by 0.1 to the fourth, and so you get S squared is equal to 3.2 times 10 to the minus 16. And then you take your square root and you get 1.8 maybe times 10 to the minus 8. Let's see what you get. You get, 1.8 times 10 to the minus 8. All right, so that is your molar solubility. All right, let's compare that to the solubility in water. All right, so let's do in water. So now you have your zinc sulfide going to zinc plus 2 and S minus 2 with the KSP of 1.1 times 10 to the minus 21. So that's 0, it goes to the right. So that's S, so your KSP is equal to S squared. And so your solubility here is going to be 3.3 times 10 to the minus 11, I'm guessing. It is 3.3 times 10 to the minus 11. That is a good guess. All right, so the reason why I did that is to see that your solubility increased by a factor of 10 to the third. All right, so why did my solubility increase? Well, it increased because your first reaction, your KSP, you're producing zinc plus 2 and S minus 2. But as soon as your zinc plus 2 is being formed from this dissolving, that zinc plus 2 reacts with your NH3. And so you are pulling the zinc plus 2 out of your equilibrium. And so it is going to the right to form more of the zinc plus 2. So it's Le Chatelier's principle. You're removing a product, and so you're shifting the equilibrium to the right, which means more of the zinc sulfide is dissolving. And to complete the possibilities, let's do this in 0.10 molar Na2S. All right, and so if you have Na2S, all sodiums are soluble. So this is 100% going to the right to Na plus, S minus 2. So this is starting at 0.1. It is 100% going to the right. It ends up at 0. So minus X plus 2X and plus X. And so you see your X is 0.10. So that is 0.20 molar, 0.10 molar. All right, and so when you put that in Na2S and you write the same zinc sulfide and you're looking for your solubility, that zinc plus 2 and S minus 2 now are initial, 0 for the zinc plus 2. But now, since we are in 0.1 molar Na2S, we have 0.10 molar of my S minus 2. All right, so it has to go to the right, plus S. You can't have a 0, plus S. And so you have S and you have 0.10 plus S, except your KSP is 1.1 times 10 to the minus 21. That is extremely small, and you're going to neglect your plus S. That S amount is not going to change your 0.10. So you have your 1.1 times 10 to the minus 21. That's equal to your zinc concentration, which is S. It's equal to your S minus 2 concentration, which is 0.10. And so you get your S value is 1.1 times 10 to the minus 20th. All right, so that is an extremely small solubility. And so you have your three solubilities for the three different choices for your zinc sulfide. If you put it with NH3, it pulls the zinc plus 2 out. You have the highest solubility, 1.8 times 10 to the minus 8. In just pure water, it's simply the square root of your KSP, which is 3.3 times 10 to the minus 11. This time, we are adding a product, Le Chatelier's principle. If you add a product, equilibrium shifts to the left, which means less things are coming to the right. And so it is going to be by far the least soluble. And that's why you got such a small solubility for that one. All right, so you have your answers, you have the explanation using Le Chatelier's principle. Then the last problem in chapter 17 was 17.70. We have Na plus, you got Hg plus 2, and you got Ca plus 2. All right, so on the test, you don't have to know any of them except for the group 1. So I will say here's group 5. And I will say here is group 2 and group 3. And we'll go with group 2. Group 2. And then the calcium is group 4. All right, so you need to know the flow chart. How do you separate these groups? Well, the first thing you do is you add HCl, and that will separate group 1. All right, and so then you're going to add to your solution here, you're going to add H2S, and we're still have acid HCl, so it's still acidic. All right, and then that's going to separate your group 2. All right, so then you have your solution here. Now you're going to have H2S, and you're going to add NH3, which is a base, and that's going to precipitate out your group 3. And then you have your solution, and then finally you're going to add either a carbonate or a phosphate, because the rules are all carbonates and phosphates are insoluble, and that will give you group 4. And then this is group 5. Group 5 are metals that are always soluble. That's your sodium, all salts of sodium soluble, all salts potassium are soluble, all ammonium, but that's not a metal, soluble. All right, so that is how you will do that. You just need to know your flow chart. You do not need to know where they fit in, except for group 1 and group 5. You have to know the members of group 1, silver, mercury, lead. All right, and then group 2, you don't need to know. I'll say we have a group 2 metal. How do we separate it? Well, you add HCl, then you will separate out the group 1s, then you add H2S with H+, then you filter, that's a solid group 2. Group 4, well, you keep going. You add NH3, you precipitate out group 3. Then you add a carbonate or a phosphate. That's how you precipitate out group 4. How do you get group 5? Group 5 is in solution at the end. It does not get precipitated out. All right, so you should be familiar with the flow chart. All right, so that is the end of the questions in chapter 17. Chapter 18. 1832. All right, diethyl ether. Solvent, okay, heat of vaporization. So the heat of vaporization is your delta H vaporization of diethyl ether and its boiling point. And it has a boiling point that is a 35.6. As soon as you get a Celsius, you should add 273.15. All right, and so the delta H of vaporization is given as 26.7. kilojoules per mole. What is the entropy change when 1.30 moles, 1.34 moles, sorry, vaporizes at its boiling point? All right, so we are at a, we're doing a vaporization. All right, and so we have your C2, C2H5 sub 2O. We're vaporizing it. And so here it's a liquid, and we're going to vaporize it, and we're going to vaporize that same formula, C2H5 sub 2O, to a gas. All right, so that's vaporization, liquid going to a gas. So we know that you have to heat a liquid to make it a gas, so we know it's endothermic, and they gave us that number, positive 26.7. What else that we see from this reaction is not only do we know it's endothermic, we also know that we're going to have a positive delta S. We have a liquid going to a gas, so we know that delta S is also positive. And so we are at equilibrium. We are at a boiling point. And so at a boiling point or at a freezing point, your delta G is 0. And so your delta G is equal to delta H minus T delta S. All right, so you have 0 is equal to delta H minus T delta S. So we have our equation for the temperature, except this time we're going to solve it for delta S. So you have add your T delta S to both sides. And remember, we solved for T. We took our delta H divided by our delta S, and then we got the temperature where the equilibrium occurs. They already told us the temperature that the equilibrium occurs. It is 0.7580, 308.75 Kelvin. All right, so, but the question was, what is the delta S? That wasn't actually the question. They also want, I'm going to find delta S, and then I'm going to give the entropy when I use 1.34 moles. And so to get my delta S, I'm going to take my delta H divided by my T. Delta H is given, although I know my delta S should be in joules, so I'm going to say 26.7 times 10 to the third joules divided by the 308.75 Kelvin. And so I get my delta S, and this is joules per mole. My delta S for this process is, when I divide those, 100, no, I didn't divide those, okay. So when I take my 26.7 times 10 to the third, and I divide by the 308.75, I get 86.5 joules per mole Kelvin. So there is my delta S in joules per mole Kelvin. But the question said, what is your delta S when you have 1.34 moles? And so you see, you have to multiply that by the 1.34 moles to get your delta S, which is 116. All right, so you get 116 joules per Kelvin when you vaporize 1.34 moles. All right, 34. All right, heat of vaporization. All right, for carbon disulfide is equal to 27.2 kilojoules per mole. All right. We want the entropy change. All right, for 1 mole of vapor in equilibrium with the liquid at 25 degrees Celsius. All right, so here we have to write a reaction. So here is our reaction. That is our CS2 liquid going to CS2 gas. All right, we already know that we have to add heat to this. We know that it's going to be endothermic. They actually give us the number, so endothermic. We would know that even if they didn't give us the number. We wouldn't know the number, but we would know it's positive. We also would know we have a liquid going to a gas, and so we also know that delta S for this process, this vaporization, is also going to be positive. All right. All right, the enthalpy of the vapor at 25. All right, so they give us the S value for the vapor. So the vapor is 243 joules per mole Kelvin. All right, the question is, what is this value? What is your entropy for your CS2 liquid? All right, well, we have enough information. Just like we did the previous problem, we know that the delta S is equal to the delta H divided by T. And so we know the delta S of this reaction. Again, we want to put that in joules. So I'm going to take my 27.2 times 10 to the third joules per mole divided by the temperature. The temperature is 25 degrees Celsius, which means it is 298 Kelvin. And I get the delta S for vaporization. And when you do that, you get okay. Interesting. All right. So you get 91.3 joules per Kelvin. All right, so I will get the right answer, but I will show you that it doesn't matter if we do it this way or the way it says. So we know that the delta S for this process is 91.3 joules per Kelvin. All right, so the question says when the vapor, okay, so 1 mole of vapor in equilibrium with the liquid condenses to a liquid. So they want the reverse reaction. All right, so if we do the reverse reaction, we have CS2 gas going to CS2 liquid plus heat. So now we know we reverse the reaction, and so the delta H is negative 27.2 kilojoules per mole. And also, when you reverse the reaction, we now know that we're going to get a negative delta S because we have a gas going to liquid. That is less disorder, and that is negative 91.3 joules per Kelvin. All right, so either way you do it, you're going to get the same answer to the question. All right, so we know they gave the value for the gas. It was 243 joules per mole Kelvin. And the question was, what is your S value for the CS2 liquid? And so we know that the delta S of any reaction is equal to the S of the products minus S of reactants. And that's why when you reverse it, you will get the opposite sign. All right, so our delta S is negative 91.3 for this reaction. The product, that is what we're looking for in this one. That is the S for the CS2 liquid minus the reactants, which is 243 joules per Kelvin. And what we do know is that this CS2 gas is 243. So the CS2 liquid is going to be less than 243. So the gas has more disorder, larger delta S, than a liquid is going to have. So in order to get rid of the negative 243, you add 243 to both sides. And when you do that, you get an S value for your CS2 liquid equal to 152 joules per Kelvin. So this number is 152 joules per Kelvin. If you do that up here, do products minus reactants, you would get the exact same answer, 152 joules per Kelvin. But the question said you have a gas going to a liquid. But it doesn't matter. Your S values are the same. The only difference is your products and reactants. So you would have the opposite sign. All right, 1836 is very simple. So that is just predict the sign of delta S. All right, and so you have two gases. I won't even write what they are. Two gases going to two gases and another gas. All you need to know is you got two gases going to three gases. And that is more disorder. Delta S is positive. For the second one, we have a liquid I'm going to ignore. We have three gases. And then we have two gases and a liquid, so 2 moles of gas. All right, so this one you have 3 moles of gas going to 2 moles of gas, only looking at the moles of gas. And so now we're going to less disorder. And part C, you've got one gas in equilibrium with the solid, 0 gases. All right, so again, you're going to less disorder. And then in part D, you have 0 gases. It's a solid on that side going to a solid, a gas, and a gas, 2 gases. And so you got more disorder. So you're just looking at the gases. If you have the same number of gases on both sides, you cannot predict the sign of delta S. For the examples here, they all had a different number of moles of gas in each one of those. All right, 38. All right, so now it says calculate delta S. So now we're not just going to tell you if it's plus or minus. We're actually going to give the number for delta S. All right, so the first one is 2 calcium solid plus O2 gas yields 2 CaO. All right, so one thing we can do is predict the sign for this one gas going to no gases. So we know the delta S is negative. So if you don't get a negative delta S, you might want to check your math because this one has to be a negative delta X. And so you look on the chart for your S values. For calcium, 4159. For oxygen, 205. 0.0, and for calcium oxide, it is 38.21. All right, so you get the delta S by taking your S of your products and subtracting your S of reactants. And so we have 2 times 38.21 minus 2 times 41.59 plus 1 times 205. All right, so you get a delta S when you push the buttons, negative 211.8 joules per Kelvin. All right, so you predict a negative delta S, you get a negative delta S. All right, so the next one, PB solid 1/2 O2 yields PBO. All right, so these should be very simple. You just look up the numbers, 64.78, 205, 66.32, and you just take products minus reactants. All right, so you've got your 66.32, that's your products, minus 64.78, plus 1/2, coefficient 1/2, 205. All right, and so when you push the buttons for that, so here you have a 1/2 of a mole of gas going to no moles of gas, and so you're going to more order, less disorder, and that number, can't read my writing, I think it's negative 101.0 joules per Kelvin. So it is negative, that is 164, yep, that's right. All right, then part C, CS2 plus 4H2 goes to CH4 and 2H2S. So here you've got 4, 5. You got 5 gases going to 3 gases. Again, you're going to less disorder. So this one also is going to be a negative delta S value. So you look up the numbers, 237.9, 130 point something, maybe a 6, not sure. All right, point something. And CH4, 186.1, and 205, 205.6. You might want to check those numbers on the chart. That's just your S values off the chart. Your delta S, when you take your S products minus S reactants, you get negative 163 joules per Kelvin. All right, then part D, same thing. So these should be very simple. C2H4 plus 3O2 goes to 2CO2 and 2H2O. All right, so you got, all right, so here's one that you would have to calculate. So here's where you have 4 moles of gas, and on the other side also 4 moles of gas. All right, so you cannot predict. So here's where you would have to do the calculation in order to find out if it is positive or negative. So you have your 219.2, your 205.0, your 213.7, and your 188.7. So be sure that you are getting H2O gas, not H2O liquid. Make sure you're looking at the phases. They will be labeled clearly. All right, and so now you do your delta S is your products minus reactants. Again, you got to multiply it by the coefficient because that is per mole. So 2 moles of that, 2 moles of that, 3 moles of that, 1 mole of that. And when you push the buttons on your calculator, When you do products minus reactants, you get negative 29.4. So it is a small negative number, but it is a negative number. Negative 29.4 joules per Kelvin. All right, so products minus reactants, those should be very simple to get your delta S of any reaction. You should be able to predict it and also calculate it. 1840. What is the change in entropy, delta S, for the reaction? All right. So the same thing. So you got your Ca, CO3 solid, plus 2H plus, going to Ca plus 2, H2O liquid, and CO2 gas. All right, and so we have no gases on the left going to one gas on the right, and so now we can predict our delta S will have a positive number. All right, so you find the numbers 92.9, 0, negative 53.1, H2O liquid 69.95, and CO2 213.7. And if you look at the previous number, so it makes a huge difference. H2O liquid is 69.95. H2O gas is more than double that, almost triple that. It is 188.7. That's just more than double, not almost triple, I guess. Over 2.5 times as large. All right, so you find your delta S, products minus reactants, and you got 1 times that, 1 times that, 1 times that, 1 times that, 2 times 0 is still 0. All right, so when you push the buttons, you do get a positive number. Your delta S is a positive 137.65 joules per Kelvin. All right, 1842. Using enthalpies of formation, all right, we're going to calculate delta H, also delta S, and then we're going to use these to find delta G. All right, so we have our reaction 4, HCN, liquid, plus 5, O2 gas, yields 2, H2O gas, plus 4, CO gas, plus 2, N2 gas. All right, so we have 5 moles of gas going to 1, 2, plus 4, 6, plus 2, 8, going to 8 moles of gas. And so we are definitely going to more disorder. So we can predict the delta S to be positive. So we're going to find delta H and delta S. Let's find the delta H first, and then we will find our delta S. All right, so delta H for HCN, 108.9 kilojoules per mole. Delta S is 112.8 joules per mole. Kelvin. All right, delta H, element in the natural state, 0, 205.0 for your delta, for your S value. Your H2O gas, negative 241.8 and 188.7 for the S value. Your CO, negative 110.5, 197.5 for the S value. And then element in the natural state, delta H is 0. The S value is 191.6. All right, and so define the delta H of any reaction. We take the delta H of the products, add those up, minus delta H reactants. Define our delta S. We take our S of our products, subtract our S reactants. All right, so again, do not forget your coefficients. 2 times this, 4 times that, 2 times 0. All right, so there's your products minus reactants, 4 times your 108.9, 5 times 0, you can ignore that. And so your delta H, when you do your products minus reactants, is so negative 241.8 times 2 plus negative 110.5 times 4. So that's my products. So the product number is negative 925.6 minus the reactants, which is your 4 times the 108.9. And that gives you your final answer when I pushed answer. So that is a negative 1361.2 kilojoules per mole. All right, so that's minus, and this is going to be a whatever 4 times 108.9. All right, so it is very exothermic. So you have an exothermic reaction. Now we got to do the same thing for delta S. All right, so your products, you got 2 times 188.7 plus 4 times 197.5 plus 2 times 191.6. All right, and so your products add up to 1,550.6 minus reactants, and that is 4 times 112.8. And 5 times 205. And so when you do that, you get a delta S of 74.4. All right, so we predicted a positive delta S. I would have thought more positive than that. All right, so this is going to more disorder. All right, so now we want to find our delta G. All right, so what we do know is anytime you have a negative delta H and a positive delta S, what you do know is that your delta G is negative at all temperatures. So it's always spontaneous, or simply spontaneous at all temperatures. So we know we're going to get a negative number. So we just need to find what that number is, and that is your delta G is equal to your delta H minus the T delta S. All right, we could have done products minus reactants because we are at 25 degrees Celsius, but the problem said do it by using your delta H and your delta S. And so negative 1361.2 kilojoules per mole minus 298 Kelvin. And we have to convert that into kilojoules, and that is 0.0744 kilojoules per Kelvin. And so now the Kelvins cancel, and you have a negative, and this is going to make it even more negative. And so they both give a negative to the delta G, so a negative, and then more negative definitely is going to be negative. All right, so we take our negative 1361.2, and then we subtract the 298 times the 0.0744. And that gives us a negative 1383.4 kilojoules per mole. All right, so of course that is spontaneous. Since we already said it's spontaneous, doesn't matter what the temperature is. Because if you tried to find a temperature, to find the temperature, remember that is your delta H minus your, divided by your delta S. All right, and if you take your delta H, negative 1361.2 divided by your delta S, 0.0744. This is in kilojoules per mole. This is in kilojoules per mole Kelvin. You will get a negative number, so you don't have to push the buttons. Never can you have a negative temperature in Kelvin. So temperature in Kelvin, never negative. All right, so there is no temperature which will change the sign of this delta G. It is always negative, always spontaneous, no matter what your temperature is. Okay, let's do 44. The free energy of formation, that is delta G, of 1 mole of compound refers to a chemical reaction for the following right through. Okay, so delta G, it's the same reaction as your delta H. Delta G formation, delta H formation is formation of 1 mole from elements in their natural state. And so you're going to have to use fractions, not every time, but many times you have to use fractions. All right, and so we want to make MgO solid. So we got to take Mg solid off the periodic table plus 1/2 of O2 gas off the periodic table in order to form MgO solid. All right, for the next one, we want to form COCl2. So this one takes the element carbon, but carbon in its solid form could be diamond, could be graphite, could be buckyball. So you should write graphite. So it is carbon graphite plus 1/2 O2 gas plus Cl2 gas is going to give you 1 mole of COCl2. CF4. Again, this time, same carbon graphite plus 2F2 gas gives you CF4. And PCl5. All right, so this is P4, 1/4 of P4 plus, we have Cl2. In order to get 5 Cls, that is 5 halves. All right, so that will give us 1 phosphorus and 5 Cls from elements in their natural state. 1846. Write the standard free energy for the following reactions at 25 using standard free energies of formation. All right, we're going to calculate this. All right, so we are at 25 degrees Celsius. All right, so the only time you can do delta G products minus reactants is when you are at 25 degrees Celsius. So you have your C2H4 plus 3O2 goes to 2 CO2s plus 2 H2O. We have to put everything is a gas. Everything is a gas. All right, and so you have 4 moles of gas going to 4 moles of gas. So you cannot predict the delta S for this one. You would have to calculate it. But delta S is not the question. The question is delta G. All right, so we look up our chart. The delta G value is 68.39. All right, elements in their natural state, 0, negative 394.4. H2O gas, negative 228.6. And so to find the delta G, it's equal to your delta G products minus delta G reactants, and only at 25 degrees Celsius, which the problem states we are at 25 degrees Celsius. So 2 times negative 394.4 plus 2 times negative 228.6, that's your products, minus reactants, and that is simply the 68.39, and then you push the buttons and you have your delta G. All right, so 2 times negative 394.4 plus 2 times negative 228.6. All right, so this gives you a negative 1246 and then minus 68.39. All right, so you have a delta G value of negative 1314. All right, so delta G is equal to negative 1314.4 kilojoules per mole. All right, and so we know that this reaction is spontaneous. So negative delta G will tell us that the reaction is spontaneous. All right, the next one, part B, Na2CO3 plus H plus goes to 2Na plus and HCO3 minus. All right, solid. Okay, so this one we cannot predict the delta S either. We're not doing delta S, but we have no gases on either side. So we could not predict the sign of delta S. We would have to calculate it using the chart products minus reactants. All right, but the question is calculate delta G. So we go to the chart at 25 degrees Celsius, negative 1048. H plus is 0. Na plus is negative 261.9. And your bicarbonate is negative 586.8. And so you simply, to get the delta G of this reaction, you take your delta G products and then delta G reactants. Take your products minus reactants, and that is your number. So 2 times negative 261.9 plus 1 times negative 586.8. All right, so your products is a total of negative 1110.6. And then minus reactants, the reactants minus a negative 1048. minus a negative 1048. And so minus a negative is plus 1048. And so our delta G for this reaction is negative 62.6 kilojoules per mole. And so again, this is spontaneous. All right, so products minus reactants problems should be very, very simple. All right, 48. 18.48. For each of the following reaction, state whether the reaction is spontaneous, non-spontaneous is written. All right. So we have part A, we have HCN gas plus 2H2 gas going to CH3NH2 gas, and the delta G is negative 92 kilojoules. All right, and so we know that this is spontaneous. Negative 92, spontaneous. All right, so the forward reaction is spontaneous. That means we have a lot of products and a very few reactants. So that means a large K value. We could actually solve for KEQ at a given temperature and we would get a large K value. All right, so here we have 3 moles of gas going to 1 mole of gas. All right, and so we're going to less disorder, so we can predict the sign of delta S to be negative. All right, so it's spontaneous. You're going to have a large KEQ. That means a lot of products. All right, so the next one in part B, it says that your delta G is a negative 173 kilojoules. All right, so again, same answer, spontaneous. Large K value. That means lots of products, very few reactants. All right. All right, for part C, we have a positive delta G. That is 479 kilojoules. So that is non-spontaneous. That means you're going to have a very small KEQ. All right, so that means you're going to have very few products. Mostly it is reactants. For part D, (110 kilojoules for your delta G. All right, same answer. This is non-spontaneous, small KEQ. That means very few products, mostly reactants. All right, then in E, it falls into our category of equilibrium. So E, your delta G value, is 2.6. All right, so you would not call this non-spontaneous. It is positive, so you want to call it non-spontaneous. But remember, when we're between a plus and minus 10, we are said to be at equilibrium. All right, which means we're going to have a significant amount of both products and reactants. We are not at the true equilibrium where delta G is 0, but we're at such a small number for delta G, we're going to have a lot of both products and reactions. So your K value is going to be very close to 1. So we're going to have both products and reactants. When you have a small KEQ, that means you're mostly all reactants. very few products. All right, so if you have a large K value, you pretty much are all products and very few reactants. When your K value is, when your delta G value is between plus or minus 10, then your K value is neither small or large, it is near 1. And so you're going to have both products and reactants in significant concentrations. All right, 1850. Calculate delta G or delta H and delta G for the following reactions at 25 using the data. Interpret the sign of delta H and delta G. Okay. All right, so for part A, we have PbO solid 2, PbO, which is a solid, plus N2 gas. That yields 2 lead solid. And 2 NO gas. All right, and so we're going to find our delta H for this reaction. We're at 25 degrees Celsius, delta G, so we can just get the numbers and do products minus reactants. All right, so here we can predict our value, our sign for S. We have 1 mole of gas here. We are going to go to 2 moles of gas on the right. Go into more disorder. So the delta S would be positive. All right. So to find the delta H, we got to look up all these numbers. Negative 219.4. Nitrogen, element in its natural state, 0 for both of those. Lead, element in the natural state, 0 for both of those. NO, 90.29 and 86.6. And this one for lead oxide, negative 189.3. All right, and so you find your delta H, products 2 times the 90.29, the other one is 0, minus reactants 2 times negative 219.4. That you get 619.38. All right, so this is an endothermic reaction. Now we're going to find our delta G, same way. Delta G products minus delta G reactants. Again, we are at 25 degrees Celsius, the only time you can use that. So it is 2 times the 86.6 minus 2 times the negative 189.3. And that is a 551.8. All right, and so it is non-spontaneous. All right, and we already predicted that the delta S would be positive. So since we had a delta S that is going to be positive, and the delta H is also positive, we know that this is going to be spontaneous at high temperature. So this will be spontaneous at high temperature when they are both positive, the delta S and the delta H. It would be spontaneous at high temperature. Again, You could say the 1,000 Kelvin is high, it's going to be spontaneous. No, you have to actually calculate. It might be, it might not be. It may not be high enough. So temperature that we're talking about here is the temperature you get when you take your delta H and divide your delta S. So it has to be higher than this temperature in order for it to become spontaneous. All right, part B. You have your CS2 liquid plus 2 H2O liquid going to CO2 gas and 2 H2S gas. All right, so we have 0 gases going to 3 gases. We know delta S is going to be positive. We are definitely going to more disorder. All right, but we have to calculate our delta H. We have to calculate our delta G. We are at 25 degrees Celsius. We can do products minus reactants for our delta G. All right, 87.7, negative 285.8, negative 393.5, and negative 20.5. Those are the values for delta H. Delta G, 65.27, negative 237.1, negative 394.4, and negative 33.33. All right, so we get our delta H for this reaction. Delta H products minus delta H reactants. All right, so we have a negative 393.5 plus 2 times negative 20.5. All right, so our products are negative 434.5. All right, minus the reactants, 87.7. All right, and then minus a negative 2 times 285.8. So you get your delta H to be 49.4. All right, so that is positive. That is an endothermic reaction. All right, so then you do your delta G the same way because we're at 25 degrees Celsius. So you take your negative 394.4 plus 2 times negative 33.33. All right, so your products for your delta G add up to a negative 461.06, and then minus the reactants, so minus the 65.27, and then minus the negative 237.1 times 2. All right, so your delta G is negative 52.13. So it is spontaneous. All right, so here we have the same result as last time as far as the signs go. Our delta S is positive and our delta H is positive. And so we know that this is going to be spontaneous at high temperature. Again, that is a very generic statement. What temperature are we talking about? Well, it's the temperature when you take your delta H and divide by your delta S. So any temperature higher than that, it will be spontaneous. It's already spontaneous. So a high temperature here is 298. That's a high temperature. The last one, 298, was not a high temperature because at 298, on the last one, we had a positive delta G and it was non-spontaneous. And so high temperature is dependent on what you have for your delta H divided by your delta S. Sometimes a high temperature is 298. Sometimes a high temperature is much higher than 298. All right, I think that we did 1854. That was completed already. 1856, 1858. I think we have done the rest of chapter 18. I'm going to post all of the worked out homework from chapter 17 as well.